Hi students, welcome to HSC Chemistry and the Organic Chemistry module. This is video number 22. We're going to go into a little bit more detail about the oxidation of alcohols. In this particular video, we're going to investigate the products of the oxidation of primary and secondary alcohols. We're going to look at some of the shorthand ways of trying to identify these. So these are some of the abbreviations you might use for primary or secondary alcohols. And what we're going to be looking at is some of the conditions associated with the oxidation of these alcohols, and also to draw out the redox reactions so we can get an understanding of exactly what's going on and put that in the context of what we previously have learned about reduction and oxidation processes. So the first thing that we want to have a look at is the oxidation of primary alcohols. And what I have here is a form of an equation that I've shown you previously. So we've talked about the fact that when we look at primary alcohols, we actually have a number of products that can be produced as a result of their oxidation. So the conditions become very important. One of the products that we get when we oxidize an alcohol is an alkanal, assuming that, of course, that the alcohol is a primary alcohol. So in this case, we have ethanol. So I'll leave the hydrogens off for the moment and just indicate the functional group. So here is the functional group. And for this particular functional group, we are going to actually change this through oxidation to the ethanal molecule, which has the double bonded oxygen as its functional group. So that's what we know happens, but how does that happen? Well, it happens through two half processes, one of which is reduction and one of which is oxidation. Now, it is possible that you'll find some of these processes actually listed on the reduction potentials, the table of standard reduction potentials that you get as part of your data sheet and periodic table. But there are ways of being able to try and work through this. And in fact, that's what we might try and do with this particular one, just to get a sense of where all of these things are. An important part of this process is the fact that if we continue to drive this process forward, we're not actually going to stop at ethanal. We're going to go through to ethanoic acid. So as I mentioned earlier, the conditions are very important. What we want to look at is the fact that the first thing, and probably the most important thing that we need to do, is look at the formula for ethanol, and to be aware of the fact that if we're going to oxidize that to this one here, C2H4O, then we're going to need to treat this as we would normally with an oxidation. So if this was an oxidation step, then we would say, well, oxidation is the loss of electrons. So therefore, electrons must also be a product of this reaction. Interestingly enough, the other thing that's very important here is that you'll see that when I look at the formula for ethanol, I have 2 carbons, 6 hydrogens, and an oxygen. But when I look at the formula for ethanal, I have 4 hydrogens, 2 carbons, and an oxygen. So I've lost 2 hydrogens somewhere. If we think about the fact that we need to make sure that all of our atoms are balanced, all of our charges are balanced, and also that we've ensured that we've got the electrons on the correct side so that we can ultimately cancel them out, then we should be able to work through some slow processes to get each of these equations balanced. So at the moment, one of the simplest things that I need to do is I need to get more hydrogens in there. Now, this is a reaction that takes place in solution. Certainly the permanganate is probably in the form of potassium permanganate in solution. So we know that there's going to be water present. And the fact that there's water present means there's not just water, but there's also hydrogen ions and hydroxide ions. Now, either one of these could be part of this reaction, except of course we know that this one also is an acidified solution. So we know that there will be some additional H plus ions present. But when you're looking at writing the overall reaction, it's sometimes helpful just to look at the simplest way of writing each of these in order to get them to balance, and then we can put them together later on. So if I already know that I need to have hydrogens in order to make sure that the numbers of hydrogens on both sides of the arrow balance, then the only forms of hydrogens I can have are H plus ions. Now the H plus ions themselves create an imbalance of charge as well as the number of hydrogens. So let me sort the hydrogen problem out first. I've got 6 hydrogens on the left and I have only 4 on the right. So if I have 2 H pluses, then I'll have another 2, which is 6 hydrogens. So now I have 2 carbons, 6 hydrogens, and 1 oxygen. So that's all good, but my charges are not balanced. So on the left-hand side where the reactants are, I have a overall charge of 0. On the right, I have 1 electron and 2 protons effectively, so therefore I have an imbalance of charge, so I need 2 electrons in order to balance these. So here is a very quick way of looking at a type of oxidation that's occurring in this particular, as part of this particular process. But of course, we can't have electrons in solution. The electrons can't just be released into the solution. They need to go somewhere. They need to be accepted or gained by another species. And that's what we need to do with the permanganate ion. That's what is going to be reduced here, specifically the manganese. So if we look at the fact that the permanganate ion looks like this, I haven't put the subscripts in, which is very lazy of me, but I need to remember to do that too. Now, of course, we need to know what this is going to produce. I've given you a little bit of a clue up here, but it is actually the manganese ion, which is a 2+ ion. I need also to remember that this process is going to involve electrons. And because this is the reduction, then I'm going to need to add electrons to this particular one. Now, my problem this time is I have 1 manganese on either side of this reaction, but I have only oxygen only on the reactant side, not on the product side. So in order to get oxygens over onto the product side, I have think again about my water molecules, and I have a choice between the water and the hydroxides. Now, if I remember that this is an acidified solution, then I know that I'm not going to have a lot of hydroxides floating around. So what I'm going to do is put water on the product side. But if I put water on the product side, I've introduced hydrogens here as well. So I also need to add hydrogen ions to my reaction. Now, we're almost there. But what we need to do is to make sure that we've got enough of all of these. So the first thing that I look at is the fact that I've got 4 oxygens here, which means I'm going to need 4 outside of my water molecules to get 4 oxygens. This now means I have 8 hydrogens, so I'm going to have an 8 out the front of my hydrogens. And the final thing that I need to do is to make sure that the charges are balanced. So on the left-hand side this time, the charge is 2+. So I need 2+ on the reactant side. And at the moment I have 8 pluses, 1- here, and a 1- for my electrons. So I don't want to mess around with the permanganate ion because that's going to change more things. So I can change the overall charge just by increasing the number of electrons. And so what I want is, if I've got 8+ and I need to be left with 2+, then I need 6 minuses. So there's 1 already for the permanganate ion, so I need another 5 electrons in order to make the 6 negative charges that, when subtracted from the 8 positives, will leave me with an overall 2 positive. So we're almost there. The only thing that we have left to do is to put each of these 2 half equations together to give us our net redox reaction. When we do that, we have to make sure that we're going to be able to cancel out our electrons. At the moment, we can't do that, so we're going to have to make some changes. What I want to do is have a common multiple. So I've got 2 and 5, so the simplest common multiple is 10. But that means this first equation is going to have to be multiplied by 5. So that's going to be a 10, that's going to be a 10, that's going to be a 5, and that's going to be a 5. The second equation, the reduction half equation, is going to be multiplied by 2, because that's going to bring my electrons up to 10. But that means 2 here, 16 here, 2 here, and 8 here. This means that now in a third color, I should be able to identify the species that are going to be able to be cancelled from these two reactions when I put them together. So there's one. The electrons are going to cancel out now because I've specifically looked at the fact that I wanted the electrons to cancel, so I've now cancelled those out. But you can also see that I have 10 H pluses on the product side of the first reaction and 16 on the side of the second, the reduction half equation. So that means I can actually cancel all 10 of those and remove 10 of those to leave me with 6 H plus ions. So going back up the top, you'll see that now I have all of the original ones that I put into this reaction for you. And now, of course, what I've done is I've taken the H plus ions and they have become part of my reaction. So they are one of my reactants. And then you can see everything that's on the product side with the numbers is as they are shown here. This is quite messy. It's a long process and it takes a little while to work through, but it's very important that we use the same principles that we used previously when we were looking at oxidation reduction half equations, and to ensure that our electrons are going to cancel, and then just to add them together like we would with two simultaneous equations in mathematics, and have everything to the left of the arrows on one side and everything to the right on the other. And of course, where you can cancel out any common factors, you do so. Just as we did with the formation of an alkanal from a primary alcohol, we can also form alkanoic acids or carboxylic acids from our primary alcohols. In order to do that, we need to make sure that we provide a longer reaction time, and we also can warm up the solution, heat it up, speed it up. It'll push it much further. When we do this, what we find is that we have ethanol here now going beyond ethanal to ethanoic acid. So these are the two compounds that are very important part of this process. And again, if we look at the oxidation, these are the ones that we're looking at. So C2H5OH, and it's going to become C2H4O2. And we know because it's an oxidation that there are going to be electrons. As we saw with the previous reaction, we have lost a couple of hydrogens, but this time we've actually gained an oxygen. So we can leave our extra hydrogens over here, but we need an extra oxygen if we're going to try and balance this up. Now I have used H pluses, OH minuses, and water molecules because when I start multiplying any of my organics, I just end up with lots and lots more atoms, and it makes it more difficult to balance. So one of the easiest ways for me to get another oxygen here is just to add a water molecule. But that's going to add an extra oxygen, but it's also going to add more hydrogen. So now on the reactant side, I have 5 and 1 is 6 and 2 are 8 hydrogens. I only have 4 on the product side, so I'm going to need 4 H pluses in order to balance those hydrogens. But I also have no overall charge on my reactant side, and therefore I need no overall charge on my product side. So if I've got 4 H pluses, then I must have 4 electrons as well. So now we've completed the oxidation, let's look at reduction. When I look at reduction, I am going through the same process that I looked at previously, because pretty much the same things are involved. So I know there's going to be H plus ions, I know there's going to be electrons because it's a reduction. I know there's going to be the manganese ion, and I also know that there's going to be water molecules as well as part of this process. Notice that if we're going to be using the potassium permanganate for the permanganate ions, then the reduction process is always going to be the same. So this is going to be an important one that you might find on your data sheet, and so therefore you can write it straight down, but it's useful to have just to make sure that you can actually balance these things up so they're making sense to you. Of course, when I want to add these two together, the way that I do that is to make sure that there is an equivalence in the number of electrons. So in this case, I have 4 and 5. So for me to get this one out, I'm going to have to multiply my first one by 5 and my second one by 4. When I do that, I'm going to have 5 here, 5 here, 5 here, 20 here, and 20 here. For the second reaction, I have to multiply everything by 4. So here I will have 4. Here I will have 32, 20, 4, and 16. Now we add them all together. But before we do that, we want to make sure that we can cancel any like terms. So the first one that I want to cancel out straight away are my electrons. Once I've cancelled my electrons, I look for some other like terms. So I have 20 H plus ions here, and I have 32 H plus ions here. So in this case, to remove those 20 will leave me with 12 H plus here. The other thing that I have is I have 5 water molecules on the reactant side and 16 water molecules on the product side. So again, I can cancel those ones, and that's going to leave me with 11 water molecules. Hopefully what you can see is that once we work through all of these steps, we should be able to get to the same set of numbers that we have at the top, which we do with one exception. So it's important that you make sure that you work through these processes so that all of your equations are balanced. Once you've completed the two half equations, added them together to get your net redox ionic equation, then you can make sure that all of the information that you have gathered together in your resultant equation is correct. And it needs to be correct in terms of both the individual atoms and the overall charges. So therefore, I'm always looking to see whether I've made little mistakes and where I can correct those. The more you're able to do that as you work through the processes, the easier it's going to be for you to pick up any little mistakes during exams. What about the oxidation of secondary alcohols? Well, the process is exactly the same as what we looked at previously. The difference now, of course, is that the type of product is very different. So where with our primary alcohols we were producing an alkanal or an alkanoic acid, now we're going to produce an alkanone or ketone. So this time we can't pick ethanol. We're going to have to pick one where the OH is on a central carbon rather than on an end carbon. So I've picked, in this case, propan 2-ol. And the product of this is going to be propanone. Working through the processes that we looked at before, of course, our reduction half equation is going to be exactly the same as the one we've looked at several times before. So now you may actually get some questions that involve using the dichromate ion, Cr2O72-, and again you may well use those, and you would do them exactly the same way. This case, in the oxidation process is going to go from a C3H7OH to a C3H6O, and an electron. So we know that that's where the electron's going to be. As we have looked at previously, I've got 3 carbons on both sides. I have 1 oxygen on both sides, but I have 8 hydrogens and only 6 on the product side. So the easiest thing for me to do is add 2 H pluses and then the 2 electrons. The result of all of this is that I end up with a series of reactions that again I can balance in the same way that I have previously. So my redox reaction in this case, doing the same things as we've done before, and again you can see as we've previously done, I'm going to have to multiply this one by 2 and this one by 5, and hopefully once I've done all of those things, if I've done them correctly, I will end up with the H plus ions being part of my reactants, my permanganate ion, which is my oxidizing agent, my organic species, which in this case is propantuol, and my product side will have water, the manganese ion, and my ketone, which in this case is propanone. These will take a lot of practice. I would expect that you will need to know these 2 half-cell reactions, the 2 reduction-oxidation half equations, and to be able to then form the oxidation, the net redox reactions for each of these different oxidations. But probably the most important thing is that you can tell the difference in both the products and conditions when we're looking at the oxidation of primary alcohols in comparison with the oxidation of secondary alcohols. A lot there to take in, so plenty of examples to help settle it in your mind, and thanks for watching.